Okay, all right. Let's see what we did last time. Last time we talked about the L'Hopital's rule. L'Hopital's rule says if you have two functions f over g, okay, and suppose that this limit f over g is of the type 0 over 0 or infinity over infinity, and the g derivative does not vanishes for x near a, except possibly at a. Then we have the limit f over g, okay, the limit equal to the limit of the ratio of the derivatives, f derivative over g derivative. Now, what you need to be careful is you should distinguish this L'Hopital's rule with quotient rule, okay? This is different from quotient rule. And we applied L'Hopital's rule to derive the several limits. For instance, the y that we used when we derive the trig derivative is the limit of sine x over x. This limit is 1. We did this use geometry to derive this limit is actually 1. But here, if we apply L'Hopital's rule, it's simply just one line, okay? Simply just one line. And L'Hopital's rule is related with linear approximation. And it's actually turns out L'Hopital's rule, we can apply L'Hopital's rule to get higher order information. It turns out it can be, sometimes we can get a better approximation than just linear approximation, okay? For instance, if we use linear approximation to sine x at 0, then we get our linear approximation we get is sine x equal to is approximated by x, okay? Comes from the limit of sine x over x is 1. However, we can do better, use L'Hopital's rule, sine x minus x over x cubed. Now this limit we find, it turns out use L'Hopital's rule, we get this is negative 1 over 6. So we get this limit is actually negative 1 over 6. So this is the near negative 1 over 6 for x near 0. So we do some algebra, then find sine x can be approximated by x subtract 1 over 6 times x cubed, okay? This turns out to be a better approximation for x near 0, okay? Here, the term 1 over 6, okay, 1 over 6 x cubed is, degree 3. It's called a higher order term, okay, higher order term. This is better, okay? This extra term, gives us more precise information than linear approximation, okay? So this higher order approximation, okay. So this turns out to be better. Now, of course, there's no reason that we stop at degree 3. Now, if you subtract that approximation, then divided by x to the 5. Here, all the powers are odd. And then this turns out to be, you can use L'Hopital's rule 5 times and get a number, So you can get better and better approximation of sine x by a polynomial. Similarly, you can do that for cosine x. You can approximate a cosine x by a polynomial, okay, of certain degree. And better and better if the degree goes higher and higher. Okay. So we can get algebraic representation of the sine and cosine x approximated by algebraic form, algebraic manner. This is, if you study calculus 2, you will have better chance to appreciate this idea, i.e. approximate a function by polynomials. Similarly, we do it for ln. Okay. Now x squared over ex. This limit is 0. Okay. This tells us that x squared is smaller than exponential function. Polynomials are dominated by exponential functions. Okay. We introduced the little o notation. Big O and little O notation. And also another conclusion that you need to know is ln x is smaller order than any positive power of x, okay? Log x is smaller or older than any power of x. Okay, sometimes, remember, L'Hopital's rule applies to a fraction, okay, f over g, of the type 0 over 0 or infinity over infinity. Now, if this is not the form of a fraction, then what we need to do is we use some algebra, try to transform it to be a fraction, transform it to a fraction. So for instance, this is a good example, x times ln x as x over 0 plus. Now this turns out one factor approaches 0, one factor approaches infinity. So one factor make it to be 0, one factor make it to be absolutely large. So which factor x is dominating? So we actually make this an indeterminate product. This is called indeterminate product. Then what we do is we flip one factor. Okay, we flip one factor. Then we flip one factor. Then we have a fraction. Okay, then we have a fraction. So here for this example, what we flip is x. Okay, you may flip the other, but it turns out to be doesn't work. Okay, it turns out it doesn't work. Okay, so we flip x. So we get this is ln x over 1 over x. Now this is you check it's infinity over infinity now. So we can apply L'Hopital's rule. When we apply L'Hopital's rule, when we take the, then we take a derivative. Then we get this is actually limit of x, negative x, which turns out to be 0. Okay. Indeterminate difference. Now we give one example of indeterminate difference. What we do is once we have certain indeterminate difference, we will try to make it to be a fraction by multiplying certain factor. Okay. So here for this example, we multiply the conjugate. So we get this, use algebra. Then we get this limit 1 over square root 1 plus x plus square root of x. This turns out to be, denominator turns out to be absolutely large as x approaches infinity. So this is limit is 0. Okay. So this example tells us that square root of two adjacent numbers, okay, x plus 1, okay, and x, their square root as x becomes absolutely large, then their square root, you know, the gap between them approaches 0. Approaches 0. Okay, now let's do this example. Indeterminate difference. Okay, so this example, limit x approaches infinity. And we have, this is a square root x squared plus x minus square root of x. Here x approaches infinity. First of all, as x approaches infinity, this is the indeterminate difference, okay? Now, square root of each factor approaches infinity, so this is of the type infinity minus infinity. Okay, as I mentioned earlier, infinity, you cannot view it as a finite number. Otherwise, there can be contradictions. So infinity subtract infinity, you cannot directly get this is 0, like finite numbers, okay? So this is indeterminate. You can get anything from infinity subtract infinity. You can get any finite number, you can get also infinity. Okay, so for this example, what we do is we multiply, we try to make it to be a fraction by multiplying the conjugate, okay? Multiplying the conjugate. So this will be, first we make it to be a fraction. So we multiply the conjugate, So this will be, the conjugate will be plus square root of x, okay? And then when we multiply, we also need to divide such that we do not change the value. So we multiply and then divide. So essentially we just multiply 1. Then we use difference of two perfect squares, difference formula of two perfect squares. So this we get square root x squared plus x squared minus square root of x squared divided by okay. Then don't forget this limit notation. Then we simplify. Okay, square root cancel square. Okay, square root cancel square. So we get x squared plus x minus x sorry, this is not that. This is minus x. Sorry, this is minus x. Minus x. Should be x, not a square x. Should be x squared minus x squared. So this is x. Okay, then denominator will be square root x squared plus x minus plus x. Limit x approaches infinity. Then we do algebra. So here x squared cancel x squared. So we have x over square root x squared plus x. Now this is infinity over infinity again. You can use L'Hopital's rule again, or you use use the example when we deal with infinite limit. So what we do is we divide by the highest power of x. We divide by the highest power. So here the highest power is x. So we divide by the highest power x, which is x. Every term divided by x. So this will be x up to infinity. So this will be x over x is 1. So this square root over x. So we can put a square root inside. So this is square root of x squared over x over now x put it into square, then we get a square root of x squared. So this will be 1 over square root 1 plus 1 over x plus 1 limit x approaches infinity. Now as x approaches infinity, by infinity limit 1 over x over 0. So this is actually 1 over square root 1 plus 0 plus 1. So this is 1 over 2. So this is 1 half. Okay, 1 half. Okay. Or we can use a L'Hopital's rule again here. We use L'Hopital's rule again. Another way to do it. If you use L'Hopital's rule, let's see. Now differentiate x derivative. This you get the thing derivative plus x derivative. Now what do you get is 1 over, if you apply L'Hopital's rule here, then you get a 1, x derivative you get 1. This you get a 1. This derivative you get twice square root of x multiply 2x plus 1. Now again, you also need to use infinite limit. It turns out to be we still need to deal with this thing by infinite limit. Okay. Use this example. Actually, we can get this infinite limit is 1 over. This is 1. This is 1. So this again we get 1 half. Okay. So this indeterminate difference. Okay, the key idea for indeterminate difference is we try to use L'Hopital's rule. Okay, L'Hopital's rule. Okay, example. Okay, now we start another case, indeterminate powers. This case, indeterminate. Powers. Okay, let's see some example. This example. Okay, this is indeterminate power. This is of the type 1 to the power infinity. 1 to the power infinity. We know here 1 to any power is 1, but here the base is 1 plus 1 over x. So the base is slightly greater than 1. Slightly greater than 1. Now the power approaches infinity. So you may ask which factor is dominating? Which factor is dominating? So in this case, for indeterminate power, the key idea is when the base and the power is both changing, okay, they are both changing. Then we take a logarithm. Then we take a logarithm so that, okay, we take a logarithm. So we take a logarithm. Take a logarithm. We take a log, okay? Take a log to both sides. And then apply the property of a log so that we can factor the exponent so that we get x multiplied log 1 plus x. Oh, sorry, 1 plus 1 over x. Okay, so we take a logarithm so that this is indeterminate product. Okay, so we get indeterminate product. And indeterminate product, we already done how to do that. So we get indeterminate product. Okay, once we get indeterminate product, and then we flip one of the factor. Okay, we flip one of the factor. So this is the key idea to do this kind of problem. First step, if the base and exponent they're both changing, we take a log. Okay, then so that we get an indeterminate product. Okay, so the key idea to deal with this idea. Take a log to both sides. Take a log to both sides. Then to obtain an indeterminate product. And then use the technique that we talked about last time, indeterminate product to do this. Okay. Okay, so now we deal with this indeterminate product. X approaches infinity, x log 1 plus 1 over x. Okay. Now as x approaches infinity, this we get 1 over x approaches 0 as x approaches infinity. Okay. Now if you let t to be 1 over x, remember we can flip. We did one example, x multiply log x. We flip. What we flip is we flip x. Okay, we flip the x. We flip the x. To do indeterminate product, we flip either factor. Okay. Sometimes it doesn't work. Sometimes it works. One factor, if you flip one factor, it may work. If you flip the other, it may not. Okay, so we let t be 1 over x. So this is we flip x. We multiply x. This then we can divide by the reciprocal 1 over x. So this log 1 plus 1 over x. Okay, now we can use substitution. We let t be 1 over x. Okay, x approaches infinity tells us that t is actually approaches 0. So 1 over x, substitute 1 over x by t, okay? Substitute 1 over x by t. And this example we already did last time, okay? This, if you plug in t by 0, so this is 0, ln, you see, so t is 0, ln 1 plus 0, which is ln 1. Ln 1 is 0. So this of the type is 0 over 0. Okay, of the type 0 over 0. For infinity or 0 over 0, this kind of types, then we can apply L'Hopital's rule. Okay, L'Hopital's rule. So this we get L'Hopital's rule. Differentiate. Now differentiate with respect to t. Then we get t derivative is 1, okay? Now ln derivative is, we flip ln, okay? Flip the input of ln. Then differentiate the input. 1 derivative is 0, t derivative is t derivative. Use chain rule. T derivative is 1. Now denominator is 1, so we just forget the denominator because it's 1. Now this is a rational function and is well defined when t is 0. So we apply direct substitution property of limit law, which is 1 over 1, which is just 1. Okay, now we are not done yet. Here, what we did, we find the limit when we take ln. Okay, when we take ln, i.e., this limit x approaching infinity ln 1 plus x, 1 plus 1 over x to the power x. We find this limit is 1. Remember, we need to recover the original limit. So remember, ln is continuous, so we can switch ln with limit notation. Okay, ln something is 1. Okay, ln what is 1? If you cancel ln, you take e. Okay, if you cancel ln, you take e. Okay, you cancel ln with e. So you get, if you take e to both sides to cancel ln, this is the e. Okay, so you get e to the power 1, which is the e. Remember what is e? Decimal expansion, etc., etc. So this is the e. So if you write x as integers, i.e., if n is an integer, becomes to infinity, so this limit is e. This limit is e. Okay, the base of the natural log. Okay, let's do some numerical computation to see how good this approximation is. Okay, now, okay, so we define a variable. Can everyone see the Siege Elsevier package? Okay. Okay, so let's define fx f to be 1 plus 1 over x to the power x. Okay. All right. So this limit, we know the limit of fx approaches infinity as x approaches infinity. The limit of f approaches e. Okay, as x approaches the infinity. Okay. So we just do some example. So let's see output. For instance, output f1. F1 it gives us 2. Now this is the our input is 1 is small, so the output is 2. E, remember E is 2.718, etc., etc. Let's do plug in 10. You see, it's now near 2.6. Now the limit is 2.718. Now this is close now. If you take 100, now we get 2.7 now. Okay, 2.7. Now the goal, the limit is 2.718. Now if you plug in 1,000, now you get 2.7169. Okay, the goal is 2.718. If you plug in 10,000, now you get a 2.718. Remember what is E? E is 2.7182818 blah blah blah. Okay, now if you plug in 1 more 0, you see this approximation becomes becomes slow, a little slow. Okay, you see this convergence, it get object close to the number of E, the base of the natural log. Okay. Okay. Maybe this example. Okay, limit x approaches infinity, y minus 1 over x to the power x. Okay, now we changed from plus to minus. Okay, now we use the same idea to do this problem. We use the same idea. Then the first step, the base and the exponential, they are both functions of x. Then the first step is we take ln. Okay, take ln. So we get ln 1 minus 1 over x to the power x. So we get a product of indeterminate product. Okay. Then we flip. This will be ln 1 minus 1 over x over 1 over x. Flip. Okay. Flip denominator. Multiply x. We divide by 1 over x. Okay. So what do we do is we find this limit t approaches x approaches infinity. Ln 1 minus 1 over x over 1 over x. Now you can use L'Hopital's rule directly, or you simplify it a little bit by substitution. Let t be 1 over x. So this will be 1 over x will be t. Ln 1 minus 1 over x. So this is 1 minus t. Limit t approaches 0. Okay. So x approaches 0 implies t approaches x approaches infinity. So t approaches 0 from plus direction. Okay, then we can apply L'Hopital's rule. This is you check again. This is 0 over 0 by plugging t by 0. Then you get t derivative ln 1 minus t derivative by L'Hopital's rule. Okay. Then what we get is this is t derivative is 1. Ln, okay, we flip the input of ln, and then we differentiated the 1 minus t. Chain rule, okay, chain rule. We apply the chain rule, okay, we apply the chain rule by chain rule. Log differentiation, okay, logarithmic differentiation. Now, 1 minus t derivative is 1 derivative 0, t derivative is 1 minus 1 over t. Now the denominator is 1, so we just forget this 1. T approaches 0. What it did? T 0. Okay. So this is 1 minus 0, 0 minus 1, so this is negative 1. Negative 1 over 1, so this is actually negative 1. Okay. Then we see we need to recover the original limit. So ln the thing 1 minus 1 over x to the power x. This thing approaches negative 1. Negative 1. Now if you take e to both sides, take e. E is continuous. Okay, e is continuous. So you apply e to cancel ln. This thing approaches e to the negative 1. I.e. it's 1 over e. 1 over e. Now e, remember e cancel ln, so this we get 1 over 1 minus 1 over x to the power of x, or purchase 1 over e, 1 over e. Okay, 1 over e, 1 over e. Okay. So this expression has a concrete interpretation. Now, if you choose n to be x to be integer, then what do you get? N approaches infinity. So here x approaches infinity. Now you can write in this form. This limit is 1 over e. I.e., if you use common denominator, this will be n. Now 1, you write n over n. So it's n over n minus 1 over n to the power n. This thing approaches e as n approaches infinity. Now, what is a concrete interpretation of this? Interpretation of this is the following. Okay, suppose this example. Suppose many people, in a lecture hall, there are many people, okay, attend a lecture. Suppose suddenly the audience went into a panic for some reason, went into a panic. And then, okay, before they enter this lecture hall, everyone has a hat. And then when they come into the lecture hall, they put their head somewhere in this hall. Then suddenly a panic happened. Then everyone, going out. And then because they are in a panic, they just pick one random head. Okay, they pick a random head, and then went out. And then the question is, what is the probability that everyone don't get their own head? Okay, what's the probability that everyone don't get their own head? Okay. Okay, let's consider this probability question. So here there are n people, so there are n heads. Now, for one people, the probability that he doesn't get his own head is his own head is n minus 1. So this is a possibility that he pick up someone else's head over n. So this is all possible case. Okay. So this is a probability that one doesn't get his own head. Okay. Probability. That one does not pick up his or her own head. Okay. Now, because here we have n people, now assume this is independent event for everyone, for every audience. Then this is the probability that so this is around the probability that no one gets his or her own head. Okay. Now this says the probability as n becomes large approaches 1 over e. Okay, 1 over e. Okay, this limit is, you need to know it very well, this limit. Okay. Now in general, a general formula. So 1 plus maybe x, a over x to the power b, bx, limit x approaches infinity. If you do the above procedure, then this limit is a well-known limit. So this is e to the a times b. Okay. So the above two cases are special cases of this more general example. Okay. Example. limit x approaches 0 from plus direction. 1 plus sine 4x cosine x to the power cosine x. Okay. Okay, now before we start this problem, let's see what we some idea. Remember, linear approximation says sine x is x. Okay, this is equivalent infinitesimal equivalent. Or if you add a higher power, higher order. What is cosine? Cosine x is sine x over sine x over sine x. Okay. Now cosine, the linear approximation of cosine is 1. If you add another term, x squared over 2. Okay. Cosine is 1. Sine x, so this is this is more or less 1 over x. Okay, this is more or less 1 over x. So this is essentially sine, sine 4x is equivalent to 4x. 4x near x, 4x near 0. So this is essentially 1 plus 4x to the power of 1 over x. Limit x approaches 0. Okay. Now if you let t be 1 over x, now x approaches 0. Then this implies t approaches positive infinity. Okay. So this will be limit t approaches infinity. So this is the 1 plus x, x is 1 over t. X is 1 over t. T is 1 over x, x is 1 over t. So it's 4 over t to the power t. Okay. So you see this according to what we write down. The above. Okay, this expression. Then this a, you find a is 4, b is 1. Okay, so this will be e to the power 4 times 1. So this is e to the power 4. Okay. So this is what we did this problem when we use equivalent infinitesimal. Okay, infinitesimal. Okay. Now to be more precise, if you use use L'Hopital's rule. Okay. Now we try to use L'Hopital's rule, use the routine procedure to find the answer should be e to the power 4. Okay. Okay. So what we do is the first step, of course, is take a line. Okay, take a line. Okay, the first step is take a line. Then we simplify so that we get indeterminate. So we get indeterminate product. Okay. Now once we get indeterminate product, then we flip one factor. So multiply cosine is the same thing as divided by tangent. Okay, cosine x is 1 over tangent x. Okay, it's 1 over tangent. So this is ln 1 plus sine 4x over, multiply cosine is the same thing as divided by tangent. And then we take a limit x approaches 0 from plus. So it's tangent x. This is ln 1 plus sine 4x. Now if you check, tangent 0 is 0. So now 1 plus sine ln sine 4 times 0, sine 0 you get a 0. So you get this is ln 1. This is ln 1. Ln 1 is 0. Okay, so this is 0 over 0 of type 0 over 0. So we can apply L'Hopital's rule. Tangent derivative, we get a secant squared. Okay, tangent derivative, we get secant squared. So we apply the fact that tangent derivative is secant squared. Okay, now logarithmic derivative. Okay, we use the fact that the ln fx is derivative is flip f, the input of ln, and then take the multiply the derivative of input f. Okay, so f prime over f. Okay, so here we take fx to be 1 plus sine x. Okay, take fx to be 1 plus sine 4x. Then we get f derivative is 1 has derivative 0. Sine 4x, we get a 4 times cosine 4x. This factor 4 comes from chain rule. Okay, sine derivative of the cosine. So this we get 0 plus, so we factor 0. So it's 4 times cosine 4x over 1 plus sine 4x. Okay, now this is why they find when x equals 0. Now you plug in. So you get a secant squared of 0, 1 over sine 0, 4 times cosine 0. Cosine 0. Cosine 0 is 1, okay? So this is a 4 over 1 over sine secant squared. Remember, secant x is 1 over cosine. Well, cosine 0 is 1. So this is a secant squared 0 is 1 over cosine 0, which is 1 over 1. This is 1. Okay, secant 0 is 0, so it's 1 squared. So we get that this is a, you see, this is a 4. 4 divided by 1, we get a 4. Now it's not done yet. We need to return to the original limit by taking e. Okay, take e to cancel ln. Take e to cancel ln. So we get this limit. Take e to cancel ln. Okay, so this we get ln. So we get ln 1 plus sine 4x to the power cosine x. Approaches 4, and then take e. So e to cancel this ln. E cancel ln. E to the power ln sine 4x to the power cosine x. Approaches e to the power 4. E is continuous. Okay, e is continuous. So e cancel ln. So we got 1 plus sine 4x to the power cosine x. Approaches e to the power 4. Here x approaches 0. Plus or minus. Okay. Okay, indeterminate power has actually several types. Another type is this is 0 over 0, 0 to the power 0. So three types. Type 1. Type 2 is infinity to the power 0. Type 3 is 1 to the infinity power. Now we already did this example. Okay, we already did this example. Now let's do this example. Let's start the second example. Let's do the second example. Limit, let's see, x approaches infinity, x to the power 1 over x. So this is infinity to the power 0. Okay, here the base is x, the exponential is 1 over x. The base and the exponential, they are both functions of x. Then in this case, what we do is we use ln. We apply ln to the function. So if we let y be x to the power 1 over x, then we have ln y is ln x to the power 1 over x. This is now the exponent factor out. Exponent factor out. So it's 1 over x ln x. Okay, so 1 times ln x, so it's ln x over x. Now this is a fraction. Now you see this is a fraction. This is a product, and then we make this thing to be a fraction easily. Then we have this limit x approaches infinity ln x over x. We did this example, remember? We did this example. Ln x is smaller than any polynomial, okay? Ln x is increased really slow, and it's dominated by every positive polynomial, every polynomial in positive degree, okay? So this limit is 0. Now you can also apply L'Hopital's rule. So ln x derivative over x derivative. X derivative is 1. Ln derivative is 1 over x. So this limit of 1 over x as x approaches infinity. So this turns out to be 0. Very easy. So this tells us that ln x over x approaches 0 as x approaches infinity. Now we are not done yet. Now the original function is y is x to the power of 1 over x, which is to recover. So this thing, we know ln y, ln of the thing approaches 0. Okay. Now how about a y? Now how about this thing x? This thing approaches you apply e to the thing approaches e to 0. Okay. So this e to 0 is 1. Okay. So we can conclude that x to the power 1 over x approaches 1. i.e., if you take x to be integer, take x to be integer n, then you see n to the power 1 over n approaches 1. Now this side is 1 over n to this power, to the power 1 over n, means take nth root. Okay. I.e., if you take a millionth root of a million, this number is close to 1. Now let's do some numerical experiment and see how this works. Okay, let's do fx be let fx be x to the power 1 over x. Okay, now let's see f. Now we know this limit approaches 1, so f. Let's see f10. Now 1.25, f 100. Okay, now it's close to 1 now. Now f 1000, even close to 1. F 10,000. Now f 100,000. You see it's close to 1 now. F a million. You see it's even close to 1. Okay. So nth root of n as n approaches infinity has limit 1. Okay, has limit 1. Okay, more examples. So this is the second case. Infinity to the type 0. Infinity to the type 0. Now the first case we already did one example. Okay, for these three example, the key idea is we apply ln. We did one example of the type 0 over 0, 0 to the power 0. So example, we did this example. Remember, is x to the power x as x approaches 0. Okay, example. Now the top and the base, the exponential and the base, they are both functions of x. So what we do is we apply ln. Let y be x to the power x. Then ln y is ln x to the power x. Then we factor this x. We get x multiply ln x. Okay. So we get a product. So here x approaches positive direction. Opposite the y from the right. Now we did this example x times ln x as x approaches 0. So what we did is limit x approaches 0, x ln x. Remember we flip x. This is infinity over infinity. Okay, infinity over infinity, then we apply L'Hopital's rule. Oh, sorry. Multiply by x means divided by 1 over x. So 1 over x derivative is negative 1 over x squared. Ln x derivative is 1 over x. Then we multiply denominator and numerator by x squared. Okay, multiply the thing. Then we get numerator is negative 1. Denominator is negative 1. Numerator is x. Now x over 0. Now this is well defined when x is 0 by substitution. So this is 0 over 1. So this is 0. Now remember, we're not done yet. So we know ln y, which is ln x to the power 1 over x, approaches 0. This means y is e to the ln y, which is the e to the ln x to the power 1 over x, approaches e to the power 0. Okay, e to the power 0, which is 1. Okay, e to the power 0 is 1. So this means 0 to the power x to the power x approaches 1. Okay, x to the power x approaches 1. Okay. So more examples. Now we do examples of L'Hopital's rule. X to the power ln 2 over 1 plus ln x. Limit x approaches infinity. Okay, the base and the base and exponent, they are both changing. Base and exponent, they are both changing. So this will be, we let y be x to the power ln 2 over 1 plus ln x. Okay, they are both changing. So what we do is we take a logarithmic, okay, take a ln. Now this use a property of ln. So we factor the exponent. Factor out, okay? Then we multiply ln x. Okay, now you see as ln x as x approaches infinity, ln x over infinity approaches infinity. Okay, so you see ln 2 multiply ln x, 1 plus ln x. We can divide, or we apply L'Hopital's rule. Okay, if you apply L'Hopital's rule, infinity over infinity, so this is ln 2 multiply ln x derivative. Ln 2 is constant. 1 plus ln x derivative. Ln x derivative is 1 over x. Limit x approaches infinity. Ln x derivative is 1 over x. 0 plus 1 over x. Now 1 over x cancel 1 over x. Okay, so this is actually limit of ln 2. Then you find this is actually ln 2. Another way to do this, you can also divide. So you get ln 2 divided by ln x. 1 over ln x plus ln x over ln x. So this is ln x over ln x. Divide by every term, divide by ln x by every term. Okay, divide every term by ln x. So this is ln 2, 1 over ln x plus 1. This approaches ln x approaches infinity. So 1 over ln x approaches 0. This is ln 2. Okay, this approaches ln 2. Now we showed that the thing that after we take logarithm approaches ln 2. So we get ln x to the power ln 2 over 1 plus ln x approaches ln 2. Approaches ln 2. Then we see x ln 2 cancel ln. Take a lot of the ln by take the exponential to cancel ln. Okay, so this thing approaches e to the ln 2, which is 2. Okay. Okay. This example. this example. Okay, we will use this example. Remember what we did, this E, A over X, BX. X approaches infinity, as X approaches infinity, this is E to the AB, okay? Now what we do is we construct, so how do we do that? So this is the 2x plus 5, 2x minus 3. So this is the 2x minus 3. So we can do it in this manner. 2x plus 5 minus 8. Okay. 2 to the power plus 5 minus 4. Plus 1, we write everything. Okay. So this is split. So x plus 5 minus 4. So this is the 1 over 8. You let t, okay, t minus 4. T is 2x plus 5. Okay, so this actually limit as x upper t approaches infinity is equivalent to x approaches infinity. They are equivalent. This limit t approaches infinity. 1 over 8t to the power t. Multiply this negative 4. Okay, so this finite power doesn't matter. Okay, it's a finite number negative 4. So you see this thing approaches 1 to the power negative 4. This thing we apply the, we apply 1 over e to the x, a to the x over bx. This thing approaches e to the ab. So you see, we take a is negative 8. Take a to be negative 8, b to be 1. And then x to be t, x to be t. Then this actually e to the negative 8 times 1. Multiply 1. This is e to the negative 8. Okay. Then we are done for this problem. Okay, any questions about this problem? This limit. Or you use a general procedure, take a line and then use L'Hopital's rule. So if you take a line, use L'Hopital's rule, then you do the following. You can also apply L'Hopital's rule. Take a line, then you get 2x plus 1. Line, okay, so you get a line 2x minus 3 over 2x plus 5. Okay, then you what we do is we divide multiply 2x plus 1 is the same thing as the thing divided by the reciprocal. And then line a over b. So it's this line subject 2x minus 3 minus line 2x plus 5. Okay. Now if you differentiate, limit x approaches infinity, limit x approaches infinity, limit x approaches infinity. Now this apply L'Hopital's rule. Differentiate. Then you get 2. Then this you differentiate, you get a 2x plus 5. This is 2. X approaches the infinity, yeah. Now here x, the thing uses right, find it, it's squared, and then multiply 2. Okay. So finally, what we get is, did I get something wrong? Okay. Then we cancel. X approaches infinity. Did I get something wrong? Okay. Yeah. Okay. Okay. All right. Then what we do is we cancel the factor 2. Use common denominator. So this 2x minus 3, 2x minus 5 plus 5. Then this is, you see, this is 2x plus 5 minus 2x minus 3. Okay. Now 2 cancel 2. So this is actually negative 2x plus 1 squared or 1. Okay. Now you see limit x approaches infinity. Now this you get simplify this by algebra. The numerator will be 2x plus 5 minus 2x, 2x cancel 2x. So the numerator will be 8 over 2x minus 3, 2x plus 5. Multiply denominator, so it's negative, we put it here. Multiply 2x plus 1 squared. Okay, now you check. Now this is polynomial over polynomial of the same degree, Then if you read the leading coefficients of the highest power, okay, this ratio, the limit of this ratio is determined by the top coefficients, okay, the leading coefficients. So the degree is they are both 2. Denominator, numerator, they're both degree 2. The leading coefficients, you see, this 8 times 2x squared, you get a 4x squared. So you get a 4, the leading coefficients. Now this 2x times 2x, you get a 4. Okay, so the leading coefficients is 4. Okay, okay, so here look at the leading coefficients. Look at the leading coefficients. So this is determined by the leading coefficients for this polynomial over polynomial. Okay, which is negative 8. Okay, which is negative 8. Now we need to recover to original thing. So 1 is approaches e to the negative 8. Okay, so we take a e. Okay, take e to recover the original thing, original fraction. Okay, any questions? Any questions? Okay, more examples. X approaches 1. Let's see, x to the power 2020 minus 1 over x to the 2019 minus 1. Okay, how do we do this limit? Now, first of all, by direct substitution, it does y minus 1 0, y minus 1 0. So this is of the type 0 over 0. Okay, then we apply L'Hopital's rule. Then we apply L'Hopital's rule. Then we apply L'Hopital's rule. Take the derivative. Okay, now take a derivative. This is derivative. Now by power rule, so get 2020 degree decrease by 2019 minus 0 over x 2019 2018 minus 0, limit x equals 1. Now this is well defined. This is well defined. This is, if you simplify this you get a 2020 over 2019 x. Okay, now it's limit x equals 1. So substitute x by 1, then you get a, this is x, replace x by 1. So you get this the result 2020 over 2018. Okay. Okay. More examples. let's do this example. Okay, this example, you see as t approaches 1, t to the power 5 approaches 1 from positive direction, from the right side. So ln, so t to the power 5 minus 1 approaches 0 from positive direction. Then this is the infinity minus infinity, or negative infinity minus infinity. So infinity minus infinity. So we need to use other information to determine it. Okay, so we use the property of ln. Okay, the property of ln. So we can make this difference into quotient. Okay, remember the property of ln. Ln a over b is ln a minus ln of b. Okay. So this is so ln a minus ln b. So we can use the property of ln. So ln okay, so that we have a fraction. We get a fraction. Now the next thing is ln is continuous. So we can apply limit law with switch limit law with ln. So we apply the continuity. Ln x of this function ln. Okay, so this is then we apply L'Hopital's rule. Apply L'Hopital's rule. Take a derivative. Okay, t to the 5 derivative, then we get 5t to the power 4 minus 0, 7t to the power 6 minus 0. So you got this is a 5 over 7t squared, limit t over 1. And then plug in t by 1. So this is a 5 over 7 times 1 squared. This you get a 5 over 7. Oh, what is wrong here? I forgot this ln. So we should get ln 5 over 7. Okay. Okay. For example. X approaches infinity, x over 1, x plus 1 to the power x. Okay. We can apply L'Hopital's rule. We take ln. You see, we can also use this x a to the power bx. This approaches e to the ab as x approaches infinity, plus minus infinity. So we can write in this form. X we write as x, x equals this thing. Okay, so we can write x over x plus 1. This is x plus 1 minus 1 over x plus 1. So it's three the term. So what we get is this is the y minus. So we get a y minus to the power x. Okay, so you can write this thing as y minus x plus 1 to the power x plus 1 minus 1. Okay, x, right, x plus 1 minus 1. Then we find this limit x approaches infinity, y minus x plus 1 x plus 1 minus 1. So this is limit x approaches infinity. And then we apply limit law, okay? This part, we apply limit law, then we get a, this is the e to the negative 1, e to the negative 1, okay? If you let t be x plus 1, so this will be 1 minus 1 over t to the power of t. This approaches e to the negative 1. Now this, the second factor, x approaches infinity, so this approaches 1 minus 0 to the power of negative 1. This exactly get e to the power negative 1, so you get 1 over e, okay? Of course, we can use logarithmic differentiation. You take log, you can also do that. Okay. Okay. So another way to do that is this thing, x over x plus 1 to the power of x. Now the reciprocal of this number is negative 1 to the power of x. So this is, you flip, negative 1 power means flip. So x plus 1 over x to the power of x. Now if you split, you get x over x plus 1 over x to the power of x. So you see this is 1 over x, 1 plus 1 over x to the power of x. This of course approaches e, okay? This approaches e. Then the reciprocal, take the reciprocal, approaches 1 over e, negative, okay? Okay. We have 2 minutes. Okay. Okay, I don't think we have enough time for one example now. Let me quickly make a remark of L'Hopital's rule. Some history of L'Hopital's rule. I did not mention. L'Hopital's rule is not first discovered by L'Hopital. So L'Hopital was a French. He was French, and he has some business. Okay, and he was rich. Then he hired a private tutor called Bernoulli. Probably you may heard of the Bernoulli. Bernoulli has a family. Is a family. He has a family of mathematicians. Okay, this Bernoulli family produced many mathematicians named with last name Bernoulli. And this L'Hopital hired a private tutor, Bernoulli, and Bernoulli taught L'Hopital calculus. And this L'Hopital's rule was discovered by Bernoulli. But somehow they have some trade between Bernoulli and L'Hopital. So in some sense, L'Hopital's rule was bought by L'Hopital from Bernoulli. And actually, L'Hopital wrote the first textbook on calculus. And it turns out the first textbook by L'Hopital was written by Bernoulli. After 100 years after the first publication, the first version of calculus book, and then the Bernoulli family claimed copyright from L'Hopital family. So this is actually interesting history between Bernoulli and L'Hopital. Okay, maybe we just stop here. Next time we may talk about explain how we actually derive L'Hopital's rule. Any questions?